Sorry, I didn't realize I was in
Okay.
mute. Am I audible now?
Yes.
Okay, sorry. So the synthesizable variable in system Verilog are arrays. It's a 4-state variable. It can take 0, 1, X or G. And then we have an integer. Integer is a 32-bit variable. Again, it's a 4-state. Then logic is a variable. Like if it's not used in module input and output, then it's a variable with a 4-state. Again, 4-state values. Then bit is again inferred as a 2-state variable, and it can be user defined. The size of the bit we can declare as many, like the width of the bit can be as much as we want. Then they are byte, shortened, int, long int. Again, these are 2-state variables which are 8-bit wide or 16-bit, 32-bit or 64-bit wide, or all respectively. So as per the need, we can use it in our test bench or in design, like how long we want it to be. So you probably may be finding it like it's very much related, similar to Verilog. So yeah, just to link you with the Verilog concepts and what have changed compared to Verilog, I need to touch these topics. So yeah, we'll quickly go through them. So the logic keyword is not really a variable type, but in almost all context, logic will infer a res variable. Because of this inference, the logic keyword can be used in place of res, letting the language infer a variable. So basically, what it's telling is like use logic wherever possible. You don't have to really care about it, and it will take 4-state in most of the places, and it will be declared as a res. So be it FSM or be it combination logic, just use a logic keyword to declare your wires or signals or anything. Then the bit, byte, shortened, int, and long int types are only to store 2-state values. Then synthesis, but there's again a difference between synthesis and the simulation. Okay, simulation is what you run in like even simulation is basically you run your design, the RTL. So RTL is basically when you code your design in the one of the hardware description language. When you run that, then this probably will be taken as a 2-state variables. But when you synthesize it, so when you create a netlist, okay, I hope you guys know what netlist is, but for those who doesn't know, so when you write your design in a hardware description language, VHDL or Verilog, now to do a static timing analysis or layout or placement, whatever is like after the towards the lower, like the next VLSI design flow, next step of the VLSI design flow. So you have to synthesize that design first. So you have to create a netlist. So netlist is basically in your representation of your design which you wrote in SDL in terms of AND gate, OR gate, and like these basic primitive gates. Now, when we have the netlist, then we do a system Verilog, like static timing analysis and placement, routing, power analysis. So at that point of time, everything is a 4-state because anything can be X, 0 or 1 or X or G. Okay, so basically this is the difference you need to understand. When everything goes into silicon, now you do not have control over any of the wire. It can be X, it can be G, or it can be 0, or it can be 1. So for most of these 2-state variables are only for simulation perspective, because there we want to make it speed of the simulation and use less memory. Because it's 2-state, then you need only less memory to for that variable. But if it's 4-state, you need more memory, right? So it will slow down the simulation. So there only these concepts of 2-state and 4-states comes into picture. Then so this is what this statement says. There's a risk of a functional mismatch between simulation and synthesized implementation, because synthesis doesn't maintain the 2-state behavior. So it's all about simulator. Simulator is the one who maintains 2-state behavior, because simulator will do anything we tell to simulator to do. But in real silicon at gate level, it's all we cannot control those things. So this is the difference between 2-state variables between simulation and the synthesis. So in synthesized netlist, so after synthesis we get the netlist. So synthesized netlist will act like a real silicon in terms of timing, in terms of power, or in terms of the values of the variables or the wires. So no matter what we declared, it doesn't come into picture after synthesis. So it's only for simulation. Okay, then moving to the arrays. So these are you probably have heard of array in different languages, C, C++, and Verilog. So vector is basically a packed array. Okay. So what do you mean by packed is when you declare, if you see here, let me bring that pointer. Yeah. So if you see here, if you declare a logic and a variable v, okay, and then if you declare the array 3 down to 0 in front of before the v variable name, then this is called a packed array. Okay, but when we declare a packed array, it's a contiguous bits. Okay, so consider this as an example. In memory, okay, in memory, let's consider RAM. So if there's a 1 KB of RAM, so it will be in chunks of 8 bits, right? So you want to declare 8 bits as a packed array because it's contiguous and you always will access it in contiguous, like 1 byte at a time. So for replicating those kinds of digital logics, we use packed arrays. So it's basically contiguous bits. And so vector declaration can be used as an integral single value, a whole number in operations. So basically, you can, so basically this all the packed arrays basically will consider as a one, one variable, like or one number. So if you use this basically will take all the 4 bits into account. So if you have declared v equal to 5, then it will be stored as 0101 in this 4-bit variable. Okay, and you can add different logics variables of 4 bits packed arrays. Like you can do v plus 1 and assign to v or any other logic variable of 4 bits. Okay, so an array declaration is a group of elements of similar variables or nets. So what is array? Array is basically you want to, like, other, like in place of declaring every, like int a, int b, int c, we can declare a int a as and number of variables you want to declare, and then it's easy to access them, easy to operate on them. So it's basically a similar variables grouped together. So that is what array declaration is. And array is a collection of elements with the same data type. It's again the similar kind of statement. And this is how an array is declared: int a 03. So this is basically an unpacked array. Okay, so here if you declare before the variable, it's a packed, it's contiguous, and it's similar type, and you can slice it. We'll see, we'll understand. I'll explain that what do you mean by slicing. And this one is again an array, but it's a unpacked array. So you can declare like int a, like you can access it like af0, af1, af2. Okay, and the dimensions of the unpacked array will come after the name of the variable. So this is how unpacked array is. So af0, 1, 2, 3, it can be more, it can be either in the adjacent memory locations. In if you think, so you also have to think from the simulation perspective how these like how these variables take the memory in the how these variables are allocated memory in the simulation, because sometimes this will help you debug or failing test cases also, because what happens in some of the cases, there are issues in the test bench and you need to debug it. So you need to know how these arrays are declared and how these are allocated in the memory, because sometimes your lack of understanding of the packed and unpacked array will cause issues in the test bench itself. So here is a combination of both packed and unpacked array. So I have declared an LUT which is 8-bit wide, and it has like 256 elements. So it's basically, you can consider this as a memory of 256 bytes. Okay, now if I do LU2 0, then if I want to access, if I access this with LU2 0, I'll be basically accessing 8 bits at a time. Okay, so basically I'll be accessing 1 byte at a time. So this is how memories are usually replicated in the system Verilog or similar other languages. But you cannot, so the advantage of packed is you can access 8 bits simultaneously. But here, if you looked at the unpacked one, you cannot access 0 to 256 simultaneously. You have to access one by one each of them. Okay, and the unpacked side, the 8 bits, you can even slice it. You can use like 7 down to 3 also. Like you can just, you want to access only 4 bits, so you can consider this as like, you know, 8 wires coming from the from any logic, and now you can use all the 8 wires together, or you can use 4 wires together, or any of the wire from this 8 bits. Okay, so yeah, this is how, like, and also I advise you to, you know, imagine this from the digital electronics perspectives, how this language of the code that you have written will synthesized, like what will be the corresponding synthesis when the simulator is synthesized. Will it be an FSM, will it be an adder, will it be a wire? So it will help you understand the language much better. Okay, and here if you can consider, if you see this RGB is a 3-dimensional array now of 8 bits. So it's like 16 by 16 by 16 array with, and each element of the array is 8 bits. Okay, so this can, you can think of, you know, monitor screen. Okay, so let's say whenever a GPU writes, no, GPU will, let's say you are playing a game. Okay, this is a real kind of example I'm giving you. Let's say you are playing a game and there's a GPU that will process the game. Okay, now GPU will be sending the images into the screen, right? So what will GPU be sending into the screen? GPU will send the RGB values. Okay, and for each pixel. So now consider this 16 by 16 as a pixel, like let's say there's only 2-dimensional array. So 16 by 16, like, so if you have a screen of 256 pixels, then 16 by 16 is the array size for that memory of the pixels. And now each pixel will be represented with an RGB value of 0 to 7. So basically, yeah, so the 8 bits is used to, is a single unit. You can consider it as an integer or anything, and you can access individual bits if you the way you want to. And then the right hand side is an unpacked array, and you have to access each element at a time. It can it can represent a single memory location or a single pixel or anything else, anything you want it to represent. Okay, any question you have until here? Okay, so the packed array is used to model a vectors which is made of 1-bit bytes. So it starts with 1 bit, and you can make it as much wide as you want. It can be 7 down to 0, 15 down to 0, 100 down to 0, whatever you want it to be. And it's also useful in accessing the subfields. Like if you want to access 0 down to 10 only, then you can access it in the from packed array. Okay, then unpacked array are used to model an array of different data types, like array of bytes, array of integer, real, unpacked structures, unions, like array of anything. It can arrays, like where you typically want to access one element at a time. So there you will use an unpacked array. Like if you, for example, in RAM and ROM, you will always access one memory location at a time. So there you will use an unpacked array, but every memory location will have some maybe 8 bits or 16 bits. So there you'll use an unpacked array to represent those one memory location of 16 bits. Okay, so for, like this is an unpacked array, byte M 040 down to 4095. So it represents a memory location of 4096 bytes, which means 4 kilobytes. So if you represent this, if you like
Hello, sir.
want to. Mhm.
Sir, can you explain this example one, this logic 13 down to 0 and 15 down to 0? I'm not getting. On right, left hand side, I have seen only one. matlab, That I'm
Sorry,
confusing.
can you repeat your question?
Sir, this one example one in fact that you have given now. Before
Mm-hmm.
packet, you have given two vectors on left hand side.
Mm-hmm.
Um, so, like, it should not be. I'm not getting it how it is. Miss, can you explain this?
So this basically is telling that there is a unpacked array of 16 by 40. Okay, it's kind of 2-dimensional unpacked array.
Sir, is it unpacked or packed? Because
sorry,
it's
I got confused. It's a two-dimensional packed array. Yeah.
Okay,
So,
sir. And what if and sir, what if 13 down to 0 will be on the right of the packet, then it will be same scenario or
it
what?
will, it's look, see, now these all, like, if you, in terms of number of elements, it will be same. Okay, but if you, it's all different from the memory perspective, how it's aligned in the memory. Okay, if you with, like, with the current let me, edit it and I'll show you. 1 second. Yeah, so let's say the other thing what you are saying is 15 down to 0 packet, then maybe 40. Okay, something like that, or 39 down to 0, whatever, you can write anything. So in this first example, it will be continue. You have to think from the memory perspective, how this variable will be allocated memory in the simulator. So this will be contiguous, like it will be side by side. This 15, so it will have like um, 0, 1, 2, 3, and so down to 15. And then again, next line will be like, in the RAM, it will be, the memory allocation will be like this, contiguous, 0 to 15. And then again, in the next line, it will be 0 to 15, 0 to 15 till 40. But in this case, it will be 0 to 15 for element 0. Then again, element 1 will be given 0 to 15. It can be side by side. It can be at a different location, depending upon how the simulator is given the memory by the CPU. So if you here, if you access the packet variable, you are actually accessing all of these bits, which is 16 by 40. Okay, like it's like 640 bits. But if you are accessing here packet 0, you are accessing only 16 bits, and you cannot access all of them at a time. You have to access only one at a time. So this basically is telling that this, each variable is 16 bits. Here it is telling that each variable is 16 by 40 bits. Okay, this is the difference, major difference here.
Sir,
Let's say,
for okay,
let's
sir.
say if you declare like this. So here each packet variable is 16 by 40 bits, and here each packet variable is 16 bits. That is the difference. Okay.
Okay, sir. In first case, each packet will be of 16 by 40 bits. So, sir, how to access it means like in calling or like in whenever we will use it. So, how to index it? Like in second case, I know if you want to call like whatever packet two, then we will write packet in square bracket. We will write two. But in first case, how we will
It's
call
similar.
it?
So yeah, it's good. It's a good question actually. In terms of accessing, it's always like this. You'll access 15
No,
down
they,
to 0.
huh.
So when you do 15 down to 0, you'll be accessing basically, like, you are accessing all of it. So when you access the packed array or the unpacked array, it's in the same way. There's no difference when accessing the packed and the unpacked array. Okay, you have to write on the right hand side.
Oh, okay, sir. No, like in unpacked array, it is easier. Like if you want to access like any like six yeah, six packets, so you will write packet and in a square bracket six. But in packed, that one is like if you want to only one packet. If you any packet you want to access, then how you will write it?
So you'll be
Means
accessing
you
like
have.
this. Yeah.
So this is just one. For
Yeah.
other part, we have to also, I guess,
So,
use something.
so this is what you are saying, right? Unpacked array.
Like, for packed array, we have to also give
Sorry, packed array. So
for two indexes will be there, no?
yeah, yeah.
Like,
So see, this is how we are accessing it. Sorry, this is how we are accessing it. This variable. So while accessing, it's kind of similar to the unpacked array. Okay.
so can you zoom it? Means it is not properly visible.
Can you see it now?
Yes, sir. Yes.
So in terms of accessing, it's similar to unpacked array. Okay, but it's only in terms of the memory alignment and allocation and the features like slice access. You can access here only 5 down. You can say I want to access only 5 down to 1. You can do that in case of packed array. You cannot do that in case of unpacked array. Okay.
Okay, sir. Okay.
So
And is there any use, the practical use of this kind of packed array
yeah,
means
we just
multiple
discussed,
time?
right?
No,
Multiple
for unpacked, you discussed like for unpacked, if there are two, like 15 down to 0 and 15 down to 0, then we know that it will be for a like two-dimensional picture having a certain number of pixels. But here, I'm not getting any use cases.
no use case of like two-dimensional. I can't say as of now. But if it's a one-dimensional array, like consider this.
That I know.
Mhm.
That is like it is one-dimensional array, so it has some use. But
Yeah.
two-dimensional,
So
that is.
here it can, you can consider this as a memory of.
This is
Mhm.
memory, sir.
Two-dimensional, I haven't come across any real
Uh,
use case as of now in the
that's why
industry.
I asked question.
Mhm.
Means you have given an example now, but
Yeah, yeah.
I cannot
So
think of
real use
any.
case, yeah, we really need to figure out. We can use it. Like if we want to use it, we can use it. We can create a use case around it. Like from the verification, see verification doesn't care about synthesis, so we can create any use case from the verification perspective. Yeah, from the design, I'm not very sure if designers like if it is really useful to designers. So see this, it's not necessarily like for the designers. It can be for the verification also, right? And yeah, maybe it's not so useful in design, but verification, it doesn't really
So
matter. We
it
can
was
use it.
it was confusing, bit confusing. That's why
Correct, correct.
I asked
Yeah,
question.
yeah. Like see, yeah, it's quite confusing here because it's very hard to figure out, you know, the difference, real use case difference between the packed and unpacked array. But yeah, as like if you take an example of a memory, then it becomes little clear. But then if you go to two-dimensional array, then there's an hardly a use case to that, so it becomes again, yeah, confusing. I understand that. But if you want to really create a use case, you can always create a use case in test bench, because test bench really doesn't care about synthesis. Like it doesn't have to create RAM or anything, right? So you can create a use case just to create a scenario. But a real use case in terms of silicon, I have never used any designer. I have never seen any designer used two-dimensional packed array. So yeah,
Okay,
from
sir.
the
Okay, got it, sir. Got it.
yeah, from design perspective, there may not be any real use case as such. Okay. Yeah. So any other question until here? Then okay, let's move to the next one. So user-defined data types, we can have a user-defined data types like we have in C. So to create again a higher level of abstraction. So you will see this term, you know, higher level of abstraction everywhere. Because of the complexity, we just want to hide the complexity, and we just want to create abstraction over abstraction. Now in the industry, there's so much of abstraction now, it will take years to understand the test bench itself. Like I have been working on a test bench for 1 year now, and it's still not understood because it's so much of level of abstraction and complexity. So yeah, so system Verilog can add a new data type for modeling different system and architectural level designs. Like if you, let's say if there's a FSM, and you can name an FSM like anything, right? Different status of the FSM, like you can give a name to an FSM state. So you can you can model that using as user-defined data types, and this adds ability for the user to define new data, new net and variable types. So and for this we use type def. So for using type def will allow users to create their own data type, and this is basically not creating a new data type. It's just like renaming a existing data type. Maybe it can be an primitive data type, like you can rename an integer to your name or anything like that, or you can create a complex data type, and like for example an array. You can rename an array of bit of 8-bit wide and 8-bit packed and 256-bit unpacked. So you can rename it as memory one, and you can create an array of memories. So you can use for that purpose also this type def. So yeah, so basically type def allow design discretion to be parameterized, like it helps portability and enhances readability, because you rename those as per the use of the byte. You can rename a logic 7 down to 0 variable as a memory, so it will it will helps readability, helps in understanding, and definitely better documentation. And there's an example here. This is a very basic example. You can type def int as t-mind. So basically now writing a t-mind is as good as writing an int. There's no really you probably will never do this, but it's a possible use case. But why will you waste your time writing this? But there are real use cases also, like we'll discuss here. So for example, there's a type def logic 31 down to 0 t address. So let's say there's a design where address is always 32 bits. So why will you keep writing logic 31 down to 0? You'll just type def logic 31 down to 0 somewhere in the start of the module, and then use this t address to declare wherever you are declaring a 32-bit signal. Now let's say there's a uh, design change, and now 31 is changed to 63. You can just change it 63 here, and it gets changed everywhere, right? So you can create your own data types, type defs, or data types to actually model what the design is doing, the intent of certain signals or intent of certain FSMs. If let's say there's an FSM onto uh, replicate to model the different states of the, let's say, a lift, with a chip in the lift, and a lift goes up, down, or so to model that, you can say it's in idle state, or it's in busy state, or it's in working state. So you can give those special names to them. So yeah, for and similarly you can create a type def logic 31 down to 0 as nibble, and use that type def in different parts of your design. So it's more readable, and it helps your design to be more portable also. You'll really understand this when the designs are complex, and it is used across projects, and then some of the engineers, they'll code it and then leave, and then there's someone else coming it. So if you use this kind of coding practices, it will help you and anyone who's replacing you to understand the design quickly, or the test bench quickly. Yeah, so here for example, so let's say if you use a if def 2 state, if you then you can define type def bit d type, and you can, if it's a 4-state design, then you can use a logic, and now use the d type and different places in the design. So basically, what is the intent here is the reusability of the code. This part of the code is reused based on the intent of the simulation. So if def is basically a directive that will tell you, like, whether you want to compile this or this. Okay, this is what you give during the simulation. When you run a simulator, like consider a VCS, a Synopsys VCS simulator, then you can say, okay, I'm defining a 2-state variable. Now when 2-state is defined, then what will simulator do is, it will, so since this inside if def, it will compile the first line, and it will not compile the second line. So basically it will take first line into account, and now the d type t is a bit type, and now everything will down here that has used d type t is a bit type. So it will basically help us do the reusability of the code into different intent of the verification engineer. So based on our intent, whether you want to simulate the test bench as a 2-state or 4-state, we can just based on this 2-state, we can change the behavior of d type. So this is again useful. You can just now whenever you want to change, you just have to change here. You don't have to touch anything down in the code here. So these are some of the use cases of user defined data types. Then yeah, this is the last topic for today. I haven't so we'll complete the data types today, and then we'll look into other topics in the next class. So enumeration data type. So this enumeration data type is mostly used in, I have seen in the industry, is mostly used in FSM states. So FSM, you can declare different FSM states as 0, 0, 0, 0, 0, 1. But imagine, like, some designer has coded an FSM with 0, 0, 0, 0, 0, 1. But the next designer who comes and replaces him, will he really understand what that state means? So you want to use, enum data types. So red, green, blue. You'll understand what's the intent of the design. Now, if any FSM is in red state or green state or blue state, we'll know what is the, like what is the intent of that state on the FSM. Or consider like again a pixel kind of example. If I give 1000, this variable, some variable 00, I'll not understand whether it's red or green or blue, right? But if there's a name to it, we'll understand it very quickly. Yeah. So this enum data types, again, given the complexity of the design and test bench, these are very useful to help communicate between the engineers, because it's whenever you in the real world, it's very, it's not so humpy-dory. Like when you come in the industry, the specs are blurred, the specs are old specifications, the design is not so commented, and it's not there's no document to it. You have to go through the code and you have to understand it. So this is the place where these enums and data type defs comes very useful. So yeah, so enumeration data type is declares a set of enumeration literals. So it's basically like in place of writing 000, we are just saying it red, but the simulator knows it's red is equal to 000, and we don't have to think about, we don't have to care about it. We just use it. We can just focus on what the intent is. So enumeration types provides a means to declare as an abstract variable that have a specific list of valid values, and then each value is defined with a user defined name or label like red, blue, and green in the following example. So we give a label to all the values, and the values is abstracted. We just focus on the label and use it in different places in the design. Okay. Yeah, so again, this is another example. So we'll look at one FSM code quickly and then I'll wind up today's session. We don't have much time, also 6 minutes left. So consider this define. We have used multiple defines here: fetch, write, add, sub, mult, divide, and shift and knob. And we have given different values to it. So define is a way to give a name to different values. There's another like enum. There's another way of using define. Okay. Now we have declared a module controller with an output variable read and write, an input via instruction, clock, and reset. Okay, and then we have declared 3 parameters: wait, load, and store. So here we have used parameter, but we could have used enum also. So consider we can replace, like imagine this as an enum wait, load, and store. So wait will be automatically 0, and load will be 1, and store will be 2. Then this is an FSM where the state is the current state and the next state is the next state variable. So whenever we have a pauses of the clock, state will go to the next state, and whenever we have neges of this reset, then state will go to the wait state. So wait state is basically the idle state. Otherwise, it will be at the load or store states. Okay. Now, depending upon the state, whatever the state variable is, the next state will be, so the transition of the FSM will be from the wait to load, load to store, and store to wait. So it's a cycle kind of transition happening. And then based on the instruction, which is the input variable, inputs wire, if the state is load and input is fetch, read will be 1. And if the state is store and the instruction is wire, write will be 1. So see the intent here. We haven't used 0 1 1 0. Now it's so easy to understand. If the instruction is fetch, will be read 1. Let's say if you have written here 0, and we have to go back and see, okay, if it's a very long code, long file, and maybe these defines are defined in some other file, we have to search that file and see what fetch, what 0 means. Now, but here, as when we are using fetch, we don't have to care how fetch is mapped, whether it's 0 or 1 or 5, we don't care. Okay, we just know that, okay, the instruction is fetch, and we know the intent of the design here. So when it's in the load state and when the instruction is fetch, we have to give a read is 1. So intent is very clear from the design. But if we haven't used fetch and if we hadn't used this load, so what we would have done is state is equal to 1 and instruction is equal to 0, then read equal to 1. But then if the someone who has coded it will know it, but someone who has not coded it will like it will be nightmare for him to understand if there are so many files and he has to figure out what state 0 means and what instruction 0 means. So basically these enums and type defs and defines and parameters helps in the readability and the reusability of the code. Okay, I think yeah, that's all I have for today. I hope this was useful to you. If you have any questions, you can ask me. And there was someone who was asking question in the beginning, right, regarding verification. You can ask me now. Yeah.
Sir, one question is there.
Yeah.
Sir, in the data types, you were explaining some output. So you said that it is 4 state. Although it was not defined logic or bit. So how it is 4 state? Can you open that slide?
Okay. 1 second. So it's basically inferred. Like if you don't define it, it will be inferred like 4 state. Wait.
Okay. So by default, if nothing has been mentioned, then it is 4
Yeah.
state.
Right. It will infer as logic. Okay.
That thing, that output O1.
Yeah. So if you do not declare anything, it will be declared as a, like it will infer, the simulator will infer it as a 4 state.
Okay.
Okay. Any other question from today's session?
Yes, sir. Sir, today's session is a very good, sir. And here I want to ask, like, C and comparison of C and the system Verilog, sir. Again, we are going, C is like similar to the system Verilog, right? Then
I
why
won't say
we
it's
are
similar. So yeah, it's a very, very good question, I would say, because C, first of all, C is not similar to system Verilog. System Verilog has classes. C doesn't have classes, right? A very simple comparison, simple difference I'll give you. C is like very much close to the memory. You have pointers and all those you can play with. But C plus, the system Verilog is very close to C++. It's not close to C. So you have classes, you have abstractions, inheritance, and objects. All those things are here. Okay, so it's not C. And the other thing is, it's also not C++. It's combination of Verilog and C++. Verilog is used to model hardware, and C++ is software. And system Verilog is combination of hardware and software. So the hardware part is mostly used for design, and the software part is mostly used for test bench. Because see, ultimately we want to synthesize the design, right? We want to create a silicon out of it. So we cannot use C++ because we cannot synthesize it. By synthesize, I mean changing the RTL to, it's going to complete, the session is going to finish. I don't know if you'll join again. So we can discuss the next session also. So basically you want to synthesize it. So you want to use Verilog part of the language. But again, you want to use different level of abstraction. So you want to use classes which is used in the test bench. I hope I answered your question. If not, we can discuss this in next session also.
Okay, then, so should we end the meeting? Okay, then, so we will take next out in the next session.
Yeah, we'll discuss this question again in detail in next.
Sure.
Okay.
Yeah. Okay, then. Thank you, sir. Thank you, guys. Thank you so much.
Okay, thank you, everyone. You can post the questions if there's anything else, or we can discuss.